Hello all, welcome back to Sri Sai Tech Edu YouTube channel, Read, Lead, Success. I am dealing with the subject Network Analysis and Control Systems. I have already uploaded all the videos related to Module 1 to Module 3 in my channel. If you have not watched, please do check out. In Module 4, I have already uploaded one topic video. Now, with the new topic, we will start this video. I have already done introduction and time response of first order systems in the first video. In this video, I will cover the time response of second order systems. Time response of second order systems. In first order systems, we are seeing that the transfer function is what? 1 by 1 plus st is the transfer function. Right? In the second order system, we will see what is the transfer function. Consider the second order system. This is the second order system. The closed loop transfer function C of s by R of s of the system is given by. Order why it is called second order, because if you see in the first order system, it is 1 by 1 plus st, means s is what? There is no power, s power 1 it is, so first order. Here if you see, it is s square, so it is known as second order system. You are understanding? Second order system, we have the transfer function as omega n square by s square plus 2 into xi omega n s plus omega n square as the transfer function. You need to remember this for sure. On this, there are some problems also which I will do later. See, this is the important transfer function you have to remember. This xi is known as the damping ratio or damping factor. It is damping ratio or damping factor. Omega n is what? Undamped natural frequency. Omega n what? Undamped natural frequency it is. Okay, this is the second order system. As you know, this is input, output, this is the feedback, and this is the error signal, and this is the second order transfer function. Okay, this form is called the standard form of the second order system. This is the standard form. The dynamic behavior of the second order system can then be described in terms of what? Xi and omega n. There are different behaviors, dynamic behaviors of the second order system. We will see now that based on Xi, that is damping ratio, and as well as undamped natural frequency. So if you see here, Xi is 0, means the damping ratio is 0. The poles are purely imaginary on the and lie on the j omega axis. What it is if you take the quadrants like this is called as S plane, and this is called as minus S plane, this is plus S plane, and this is plus j omega, and that is nothing but imaginary axis, and minus j omega, this is also imaginary. If you see, the poles are purely imaginary, lie on the j omega axis, which is when xi is 0, nothing but damping ratio is, if you get 0 in the answer, the system is then called what? Undamped. The transient response will not die in this. Okay, so with steady state response, transient response also will be there. It is purely oscillatory. It is called purely oscillatory. In questions they may ask, they give some equation where you need to find the values based on the equation. If you get xi as 0, then it is called what? It is undamped. You should find the answer, it is whether undamped or it is purely imaginary. So and it is purely oscillatory. You need to write in this way. If 0 less than xi less than 1, if xi is lying between 0 and 1, which is more than 0, maybe 0.1, 0.2, and less than 1 till 0.9, then the closed loop poles are complex conjugates and lie in the left half of the S plane. Now they are complex conjugates when they lie between 0 and 1. So they lie in what? This, I will mark with different color so you can understand. They lie on the left half of the S plane. This is the left half of the S plane. Understanding? The system is then called underdamped. It is called underdamped. Now the transient response is just oscillatory, not purely oscillatory. It is just oscillatory. If xi equals to 1, it came to 1. If xi is 1, if the value is 1, the poles are what? Real, negative, and equal. The system is called critically damped. Why? Because it is reaching 1, so it is critically damped. If it is more than 1, the poles are again real negative, but they are unequal. The system is called over damped. More than 1 is over, equals to 1 is critically, between 0 and 1 is what? Under damped, as it is between, and if it is 0, it is purely imaginary, it is called undamped, which is not damped. Okay, critically damped and over damped systems do not exhibit any overshoot. This critically damped and over damped do not exhibit any overshoot. In the graph, it will not overshoot. Understanding? The time response of any system is characterized by the roots of the denominator polynomial q of s, which in fact are the poles of transfer function. They are called as poles of transfer function. The denominator polynomial q of s. What is the denominator polynomial for second order? As you have seen, s square plus 2 zeta omega n s plus omega n square, right? Now, this is called characteristic polynomial, which should be equals to 0. They're telling, okay, is called the characteristic equation. This equation is nothing but the characteristic equation. What it is called? It is called the characteristic equation, which is in the denominator. You should remember this. The characteristic equation of the system under consideration is this. If you see, okay, the roots of these characteristic equations are given by the roots. How they have written is s minus s1, s minus s2. That is the roots of the equation. If xi is less than 1, then s1 and comma s2 will become minus zeta omega n plus or minus j omega n root of 1 minus zeta square. The roots, how it is. Okay, one will be with plus, one will be with minus. If you take plus for s1, then minus you should consider for s2. Okay, then this can be written as minus zeta omega n plus or minus j omega d. This omega d we have substituted for this value. Omega n into root of 1 minus zeta square. This is called damped natural frequency. Okay, damped natural frequency. If you know, if you have whatever I told, omega n is what? Undamped natural frequency, where omega d is what? Damped natural frequency, which is equals to omega n into root of 1 minus zeta square. You need to remember these formulas. They may ask questions on this. I will do this, the questions on this in the separate video. After this, there is some topic known as time specifications of second order systems. After that, separate video based on these topics I will do. Most control systems, with the exception of robotic control systems, are designed with damping factor zeta less than 1 to have high response speed. Usually, the zeta will be less than 1. So, it will have high response speed. Response of an underdamped system. Underdamped is what? Between 0 less than zeta less than 1. In this case, C of S by R of S can be written as C of S is what? C of S by R of S. You know that this is the transfer function. And if you see, if you consider in this way, S plus 2 zeta omega n plus j omega d into S plus zeta omega n minus j omega d. If you multiply this, again you get this only. Understanding? If you want, you can multiply and check. You will get this only. Understanding? Nothing but what they have done is omega d square and minus omega d square is added to the equation, so that you will get this equation. Okay. For a unit step, R of S is what? 1 by S. So, in the place of R of S, if you put 1 by S, then what happens? 1 by S into omega n square. This equation you will get 1 by S. Again, partial fractions if you take, same like first order systems how we have done, no, same. If you take partial fractions, then you will get in this way, 1 by S minus S plus 2 zeta omega n, and d so and so S plus zeta omega n whole square, omega n square minus omega n square zeta omega square. Then 1 by S minus S plus zeta omega n, S plus zeta omega n whole square plus omega d square minus omega n by omega d. This you should This is coming from the previous equations. So like that, if you do continuously, you will get this equation. You need to remember this derivation, so that if they ask, you need to write response of an underdamped system. If they ask, you need to write. Taking the inverse Laplace of this, what you will get is C of t is equals to, this is 1 and this is e power minus zeta omega n t cos omega dt. Okay, why? Because it is in the form of what? S by s plus s square plus a square. A is what? Omega t. Right? This whole thing is yes. Right? So you will get e power minus at then cos omega dt omega dt minus zeta e power minus zeta omega nt by root of 1 minus zeta square sin omega dt. You know that omega by s square plus a square is sin at. Omega is nothing. Omega by s plus omega is sin omega t. No. So in the place of s there is s plus omega zeta omega n. That's it. So if you calculate, you can get this finally. You need to practice this derivation. You need to practice. If you continuously do, you will get sin theta cos omega dt, cos theta sin omega dt. Then e power minus zeta omega nt divided by root of 1 minus zeta square. This is nothing but sin of a plus b formula. Sin a cos b plus cos a sin b. So sin of a plus b. Here a is omega dt and theta. If you again see here, omega d is what? Omega into root of 1 minus zeta square into t plus tan inverse. This theta is what? You can write as tan inverse. There is a formula for that also. Theta, that is tan inverse root of 1 minus zeta square by zeta. This is the angle formula you need to remember for t greater than or equals to 0. The error signal, even for first order systems we have calculated how it is r of t minus e of t, input and output. So e power, input is what? E power minus zeta omega nt. If you put input and output r of t minus e of t, you will get this equation when t is greater than or equals to 0. Thus error signal exhibits a damped sinusoidal oscillation. Damped sinusoidal oscillation. At steady state or at t is equals to infinity, no error exists between the output and input. When t is equals to infinite, there exhibits no error between output and input. So if zeta is 0, the response becomes undamped, right? And oscillations continue indefinitely. Purely oscillatory, right? Zeta is equal to 0. Initially we have seen when zeta is equal to 0, it is undamped. The response C of t for 0 damping case, C of t is equals to, in the place of zeta if you put 0, you will get 1 minus cos omega nt for the previous equation. Thus omega n represents the undamped natural frequency, right? So omega d is equals to omega n for zeta equals to 0. Then omega d will be less than omega n for zeta is greater than 0. For 0 it is undamped. Zeta greater than 0 is underdamped. No. So nothing but underdamped or damped. So the time response of an underdamped zeta greater than 1 second order system is plotted here. You need to see this. If you see here 1 plus e power minus zeta omega n t by root of 1 minus zeta square, and here 1 minus when zeta is less than 1. Okay, when it is less than 1, it is greater than 1. How the oscillations are happening for the underdamped system? You need to remember the diagram and need to draw. Then it is damped sinusoidal. The response reaches a steady state value of CSS. Steady state equals to 1. That is, the steady state error of this system approaches 0. The time response for various values of zeta plotted against normalized time omega nt is shown in the figure. The system breaks into continuous oscillations for zeta equals to 0. If you see for zeta equals to 0, there is a continuous oscillations, 1, 2, 3, 4. Continuous oscillations are there. Okay, this is the response curve of second order system when damped sinusoidal. As zeta is increased, the response will become progressively less oscillatory till it becomes critically damped, just not oscillatory. For zeta equals to 1, and becomes overdamped for zeta is equals greater than 1. Critically damped when 1 and overdamped for zeta greater than 1. Then figure 4.10 shows the locus of the poles of second order system discussed above. Locus of the poles of the second order system discussed above. Whatever we have studied before. With Wn, now the Wn is nothing but what? Omega n. The undamped natural frequency held constant and zeta varying from 0 to infinity. As zeta increases, the poles move away from the imaginary axis along the circular path and a path of radius omega n, emitting at the point sigma is equals to minus omega n. Okay, and then separating and traveling along the real axis, one towards 0 and other towards infinity. For 0 less than zeta less than 1, the poles are complex conjugate pairs making an angle theta is equals to cos inverse zeta with a negative real axis. If you see here, the locus of the poles of the second order system discussed above, omega n is held constant and zeta varying from 0 to infinity. This is 0 till infinity, it is going to vary. As zeta increases, the poles move away from the imaginary axis. This from imaginary axis, they are moving away. These are the poles. These are the poles. If you see, this is the pole. This is the pole. Okay, these poles are moving from the what? Moving from this imaginary. This is the imaginary axis. They are moving from the imaginary axis along the circular path as zeta is increasing. Okay, and omega n meet at sigma is equals to minus omega n. When this sigma is equals to minus omega n. And then separating and traveling along real axis on towards 0 and others to infinity. Some to infinity and some to 0. So you should just remember the derivation, how it is done, and how the graphs are drawn based on the equations and these pole locations. They ask only derivations by this, and there are some problems also that need to be seen. Why? Because I'm not sure that whether problems may given or not given, but problems are important. Why? Because they are related to this topic only. So which are related only, I do a separate video, the topics, the problems which are related to this topic. So by this I completed what? The time response of second order system in this video. With the specifications of second order system, I do a new video. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.